Welcome to the new era of video creation with Bowsiate. Today we will discuss the regularization in machine learning. Question: explain the concept of regularization in machine learning. What are the different types of regularization techniques, and how do you decide which one to use in a given model? Regularization is a technique used in machine learning to prevent overfitting, which occurs when the model becomes too complex and starts learning the noise in the training data instead of the true patterns. This is achieved by adding a penalty term to the loss function, which discourages overly complex models. Regularization encourages models to remain simple by penalizing large values for model parameters, effectively reducing the variance and improving the model's ability to generalize to new data. The goal is to find a balance between bias and variance to create a model that performs well on both training and unseen test data. Commonly used in models prone to overfitting, regularization helps in improving performance on datasets that are noisy or have many features by penalizing the complexity of the model. There are several regularization techniques used in machine learning, each with its own properties and applications. L1 regularization, lasso. The penalty term in L1 regularization is the sum of the absolute values of the model's coefficients. This technique encourages sparsity in the model, meaning it forces some coefficients to become zero. It is useful for feature selection, as it eliminates irrelevant features. L2 regularization, ridge. L2 regularization adds the sum of the squared values of the coefficients as the penalty term. Unlike L1, L2 regularization does not result in exact zeros, but instead shrinks the coefficients towards zero. It helps in reducing multicollinearity and is useful when there are many correlated features. Elastic net. This technique combines L1 and L2 regularization to leverage the strengths of both. It is effective in cases where there are many correlated features and is often used in linear models, such as logistic regression. Dropout. Primarily used in neural networks, dropout randomly disables a fraction of the network's neurons during training. This prevents the network from becoming too reliant on certain neurons, thus reducing overfitting and improving generalization. L1 regularization, also known as lasso, is an effective regularization technique when dealing with models that may have many irrelevant features. The penalty term is the sum of the absolute values of the coefficients. By applying L1 regularization, the model is encouraged to reduce the magnitude of coefficients for less important features, often driving them to exactly zero. This results in a sparse model, where only a subset of the features remain, making the model simpler and easier to interpret. This is particularly useful in high-dimensional datasets, where feature selection is critical. For example, in linear regression, L1 regularization can help select only the most important predictors, leading to more efficient and interpretable models. L2 regularization, also known as ridge regression, works by adding a penalty equal to the sum of the squared values of the model's coefficients. Unlike L1 regularization, L2 does not force coefficients to zero, but instead shrinks them towards zero. This results in a reduced complexity model that is better at generalizing to unseen data. L2 regularization helps prevent overfitting by smoothing the model, ensuring it doesn't become overly sensitive to any one feature. It is particularly useful when dealing with multicollinearity, situations where several features are highly correlated, as it prevents the model from giving disproportionate importance to any one feature. This technique is commonly used when all features are considered important and should be included in the model, but with controlled magnitude. Elastic net is a regularization technique that combines L1 and L2 penalties. The key advantage of elastic net is that it balances the sparsity of L1 regularization with the shrinking properties of L2 regularization. Elastic net is particularly useful when there are highly correlated features in the dataset. While L1 can select a subset of features, it can perform poorly when features are correlated. L2, on the other hand, tends to shrink all coefficients, but doesn't necessarily eliminate features. By combining both, ElasticNet leverages the best of both worlds: feature selection and shrinkage. This approach is particularly useful when the number of predictors exceeds the number of observations, such as in high-dimensional datasets like gene expression data or text data. Dropout is a regularization technique used in neural networks. During training, a fraction of the neurons in the network are randomly deactivated, set to 0, in each training iteration. This means the network cannot rely on any one neuron to make predictions, forcing the model to learn more robust and distributed representations. This helps reduce overfitting, as the network cannot become overly dependent on specific neurons or features. Instead, it learns to generalize better by creating multiple pathways for data processing. Dropout works by preventing co-adaptation of neurons, where neurons would otherwise reinforce each other's signals. It is especially useful in large, deep networks, where overfitting is a common issue, and it can significantly improve the model's ability to generalize to unseen data. Choosing the appropriate regularization technique depends on several factors, including the nature of the dataset and the problem at hand. L1, lasso, is ideal for sparse models where only a subset of features is relevant. It is particularly useful when you expect irrelevant features in the dataset that can be eliminated by the model. L2, ridge, is most useful when all features are important, and you want to prevent overfitting by penalizing large coefficients. It's also effective in cases of multicollinearity, where features are correlated. ElasticNet combines both L1 and L2 regularization, making it a good choice when dealing with highly correlated features and when the number of features exceeds the number of observations. Dropout is specifically designed for neural networks and is particularly useful when dealing with large and complex models that are prone to overfitting. The strength of regularization is controlled by a hyperparameter, typically denoted as L, lambda, which determines how much regularization should be applied to the model. A higher L value increases the regularization effect, causing the model's coefficients to shrink further, leading to a simpler model with less risk of overfitting. A lower L value reduces the regularization effect, allowing the model to fit the data more closely, but it may risk overfitting if set too low. Cross-validation is an essential technique for tuning the L parameter. By using k-fold cross-validation, we can test how different L values perform on the training and validation datasets, selecting the one that best balances bias and variance. While regularization is a powerful tool, it also comes with its challenges. Under-regularization can result in overfitting, where the model fits the training data too well and fails to generalize to new data. Over-regularization, on the other hand, can lead to underfitting, where the model becomes too simplistic and fails to capture the underlying patterns in the data. Regularization techniques like L2, ridge, can make model interpretation more difficult because they shrink coefficients without removing them entirely. This may make it harder to understand the importance of individual features. Hyperparameter tuning for regularization, especially when experimenting with different values of L, requires careful evaluation using cross-validation and can be computationally expensive. In conclusion, regularization is a key technique to ensure machine learning models generalize well to unseen data. By applying penalties to the model's coefficients, we prevent overfitting and encourage simpler models. We've covered several regularization techniques, including L1, L2, ElasticNet, and Dropout. Each has its specific use case based on the dataset and model type, and selecting the right one depends on factors like the relevance of features and the presence of multicollinearity. Finally, tuning the regularization strength using cross-validation is crucial for finding the right balance between bias and variance. Regularization is a foundational concept in machine learning, and understanding when and how to apply it is essential for building robust models.